So in this video, I'm going to talk about inverse trig functions and basically what I want you to get from inverse trig functions and what I want you to be able to do on our class exams. While I will be showing you graphs of inverse trig functions, you are not going to have to graph them, but you are going to need to understand why we restrict domains and do certain things with our inverse trig functions, and you can only get that from the graph. So let's kind of get started by first truly understanding what we mean by an inverse function versus a reciprocal function. And that's pretty important to understand. All right. So when we say, hey, y equals sine x, right? What do we mean by that? Well, if you think about a triangle, real simple, okay, the x is an angle, all right? The y is the ratio, because it's sine we're looking for, of the opposite side of that angle over the hypotenuse. All right, so remember that. Our classic function, y equals sine x. X is an angle. You take the sine or the cosine or the tan, doesn't matter what trig function we're talking about, you take it of an angle. So it could be sine theta, sine alpha, sine beta, whatever it is, the input. We call that the input, or the independent variable. It's an angle. Okay, that angle could be in radians or it could be in degrees, but it's an angle. Okay, what the sine of that angle equals is a ratio. Sine means, hey, from wherever that angle is in my triangle, I need to take opposite divided by hypotenuse. If it were cosine, I'd be taking adjacent over hypotenuse. And that's what that y value represents. We call it the ratio because technically, even though it is often written as a decimal, it is the ratio of the opposite divided by the hypotenuse. Okay? Now, when you take an inverse of any type of function, essentially you're swapping x and y. You're swapping your independent and your dependent variable. And when you make that swap, okay, when you make the swap, we have what we call and we essentially need to now solve for x. And this is how you would have done it in pre-calc 1 with some polynomial or rational or any kind of functions like that. One of the things you did is you swapped y and x. And you said, okay, now I'm going to have x equals sine y, but I'm going to now solve for y. And you might recall doing it this way, so this is a good way to look at it. Well, it's kind of hard. How do you solve for y when you have sine of y? Well, you negate it. You take an inverse of it. And when you take the inverse of both sides, right, it becomes sine inverse of x, and sine inverse times sine just becomes y. So we say y equals sine inverse of x. All right, this notation is really confusing. Why is this notation confusing, this -1? Because you want to equate -1 with taking a reciprocal. I understand that. So here's the problem. Yes, it is true that x to the -1 equals 1 over x. That's because x is a variable. Okay, sine itself is not a variable. So this here does not, that is not the word does. Let me try that again. Does not apply. Okay, this inverse is not a reciprocal. Okay, it's just y equals sine inverse x. Sometimes, not in our textbook, so I won't use it in class, because that is such a confusing symbol to use for inverse functions. You see something called arc sine. Okay, arc sine and sine inverse x, sine to the negative 1x, are the exact same thing. Okay, okay, reciprocal functions. Now, the reciprocal of sine x is indeed 1 over cosecant x. So it is true, and look very carefully. If I put that in parentheses and put the negative 1 out there, now that negative 1 means reciprocal. 1 over, yeah, I know what I did, equals 1 over, we know the reciprocal of sine x. Wow, sorry about that. Reciprocal of sine x is cosecant x, not equals 1 over cosecant, it's just cosecant x. So sine inverse to the negative 1 is indeed a reciprocal, so you can write that as 1 over sine x, which is cosecant x. All right, so written with the negative 1 outside the parenthesis, yes, you can look at that as reciprocal, but written as we will use it in this section on inverse functions, sine to the negative 1 x is an inverse. So what does that mean, the inverse? Well, now my x value represents the ratio. When you have an inverse, I don't know, 1/2, that value that comes after the inverse is a ratio, not an angle. That's a ratio. So what that means is, hey, what angle has sine value equal to 1/2? All right, well, all right, I can look at my basic triangle, right? 1, 2, radical 3, 1, so this is pi over 6. Yeah, sine inverse of 1/2 equals pi over 6, because sine of pi over 6 equals 1/2. Okay, so be careful with inverses. When you see an inverse function, that means, oh wait, I'm giving the ratio and I need to find the angle that has that as its ratio. Great. But the graph matters. Okay, so let's go and think about, what does the graph of y equals sine inverse x look like? Like to graph. Well, when you graph inverse functions, essentially your x and y values swap each other. All right, they swap. Well, here's the good news. Your ratios are now here, and your angles are now along the y-axis. So what angle has a ratio of 0? 0. That did not change. Remember, here's your sine graph. All right, got some real nice little curve, goes like that. Boom. All right. So the next, so that's 0. What's another? We have all kinds of Sorry. I tried to go back and erase that, but that didn't work. So let me redo that over here. I apologize for that. So again, we know that sine of pi over 2 equals 1. Well, that means that sine inverse of 1 equals pi over 2. So if I go and plug in 1 for my x, I would go up to pi over 2. And you'll find that, pi over 3, pi over 6 would be a half, right? At pi over 6, you'd be at 1/2. You'd be down at pi over 6. So they'd all be in there, all right? And it would essentially kind of keep going. And if we were to continue that, ultimately, another thing you learned in Pre-Calc 1, it's basically your sine graph flipped onto the y-axis because you are interchanging x and y values. Here's the problem. We are dealing with inverse sine functions. Do your vertical line test. The second you flip this, you totally fail the vertical line test. Fail it completely. So, how do we get beyond that and still work with inverse sine functions? Well, we restrict the domain. We restrict it completely and we say, you know what? Boom. All right. We are only going to look at angles between pi over 2 and negative pi over 2 for sine. That's it. That's all we're going to do. We're only going to look at sine of pi over 2 and negative pi over 2. That's it. All right? Because in doing that, the second we go past that, or essentially, we go past those values, it doesn't work anymore. So our sine inverse graph simply goes like this. That's the only part of the graph that we're going to look at. So what we say is we restrict the domain of our regular sine function. And so for that graph, we are only going to look at, right, there's our regular sine function, negative pi over 2 to pi over 2. And we only find the inverse sine function on that restricted domain. So when we flip it, now the domain of our inverse function does go from -1 to 1, and now our range is in that restricted part of negative pi over 2 okay, this is for the y equals inverse, but we're doing it on the restricted domain of y equals sine x, and we restrict that domain to negative pi over 2, pi over 2. So it's not that we're restricting our inverse function graph. It's a little confusing. What we do is we only find the inverse on the restricted domain of y equals sine x. That's it. We only find y equals sine inverse x on the restricted domain of y equals sine x. And that restricted domain is negative pi over 2 to pi over 2. So we go ahead and find the inverse only on those restricted domains. And we do that for all our trig functions. So that's what sine looks like. All right. We can do the same thing with cosine. So let's take a look at our basic cosine x. Basic cosine x, of course, is like this, right? Now, here's what's different. Big difference between sine and cosine. I mean, when you step back, they look like the exact same waves. But sine itself, which is over here, right, before we restricted it, sine itself is an odd function. Cosine is even. So we have to think about when we go ahead and flip that function, how do we do it in such a way, right? When we flip it on the, which is going to kind of go like this, right? So here's my 1. And then it's going to go like this. Notice, we fail the vertical line test over here. So there's my pink vertical line. Boom, failed. That was supposed to be pink. Boom, failed the test. So we restrict it differently over here. All right. I can't use this part of the original function. I pretty much, you can kind of see it here. I need to go from here to here. All right. It'll give me all a bunch of positive values and a bunch of negative values, which looks like when I convert it to this graph, it looks like that. So how am I restricting the domain now on cosine? Well, let's see. This occurs at pi. So my restricted domain for cosine is 0 to pi. So I only find y equals cosine inverse x on the restricted domain of y equaling cosine x, 0 to pi. All right. I'm not going to show the graph, but tangent is like sine. And restricted has a restricted domain of negative pi over 2 to 2. Now, a lot of this will actually make sense if you think about the unit circle for a second. And we think about our quadrants. If I restrict sine, remember, everybody's positive over here. But I'm going to restrict sine from pi over 2 down to negative pi over 2. For sine. Oh, well, that's a good thing because you got a positive and a negative. So in other words, if you're finding the inverse of an angle, you have to do it negative, you end up in quadrant 4. So you're restricting sine to quadrant 1 and 4. Oh, you can do the same for tan too because tan is positive and negative. So you're restricting tan to quadrant 1 and 4. Not a problem. Cosine. Cosine is positive in quadrant 1 and 4. So you're restricting cosine to quadrant 1 and 2. And it's good to kind of think of it that way as well because it'll help you when you're doing graphs. So let's sum up our restricted domains. So we only find inverse functions on restricted domains of the regular trig functions graph. So your restricted domain for sine inverse x is negative pi over 2 to pi over 2, which limits us to quadrant 1 and 2. Tan inverse x is the same way. For tan inverse x, we can restrict finding the inverse only on the restricted domain of the tan function from negative pi over 2 to pi over 2. Quadrant 1 and 4. Sorry about that. There you go, I fixed it. And then cosine inverse x is going to be restricted 0 to pi. And here we have quadrant 1 and 2. The other ones are 1 and 4. All right. How does that help you when solving problems? Well, it's going to help you a lot. Here's why. Let's take a look at a couple examples. Suppose I wanted sine inverse of the sine function (7 pi over 6). All right. Well, don't get confused by these problems. You know, go back to kind of order of operations. You always work inside your parentheses first. And for any of these problems, if you're not drawing your unit circle, you're going to have a hard time working out the problem. So what we're going to start with is simply looking for the sine of pi over 6. Start here, right? Start here. Forget that sine inverse just for a second. All right, well, I need to find that. I'm going to find that by drawing unit circle, 7 pi over 6. We did this before. 7 pi over 6 is down here, right? It has a reference angle. Theta prime is pi over 6. It's 1, square root of 3, 2, negative, negative. Good. All we're finding is sine of pi. So we know sine of 7 pi over 6 from the first half of this chapter is going to be negative 1/2. Great. Plug that in. Sine inverse of negative 1/2. Forget that drawing. Now we simply look at this. All right, here's how you're going to look at that. Well, number one, I can't do an inverse function over here in quad 3 because we know that sine, we can only do inverse functions when we restrict the original domain of sine to pi over 2 to negative pi over 2. So what does that mean? Well, draw another quadrant 1 or 2 or 4. Why I keep wanting to call that quadrant 2, I have no idea. I am so sorry. Quadrant 1 or 4. Because we're going to go from pi over 2 to negative pi over 2. Well, in which of those quadrants is the ratio negative? Well, it's not going to be in quadrant 1. It's going to be down here in quadrant 2. Well, I get a negative 1 over 2. Reference angle is still pi over 6. You can use that. The reference angle equals pi over 6. So what is sine inverse of negative 1/2 It's negative pi over 6. That's your answer. Negative pi over 6. We had to use 2 triangles drawn around a quadrant to get that answer. Let's look at a couple other ones. There's all kinds you can do. Let's do cotangent of sine inverse of negative 1/3. Cotangent of sine inverse of negative 1/3. Okay. Well, again, work inside the parentheses first. So forget the cotan part. We'll get to that at the end. I want you to think about, what angle are we working with for this sine inverse graph? Okay, sine inverse can only be quadrant 1 or quadrant 4. It's got to be, since it's negative, it can't be in quadrant 1. It's down here in quadrant 4. And inverse means this part is the ratio. And because it is a ratio of sine, it's opposite over hypotenuse. Hypotenuse is always positive. So it's negative 1/3. So whatever angle this happens to be, I don't even care what the angle is. I know it has a ratio for sine, negative 1/3. All I need now is the cotan. Okay? Again, it don't matter what this angle actually reads. There's no reason we need to give the answer to that angle. Because what I'm looking for is just a ratio. I want the cotan of that angle. That angle, some angle, we'll call it theta. So now I need cotan of theta. Doesn't matter what you call it. Well, cotangent, which is a reciprocal of tan, so it's not opposite over adjacent, it's adjacent. So cotan of theta is equal to the ratio of adjacent side divided by hypotenuse. I don't have the adjacent side. That's this value right here, but I can get that using Pythagorean theorem. I'm going to call that x. So what do we have? Negative 1 squared plus x squared equals 3 squared. X squared equals what's 9? It's plus 1 minus 1 square root of 8. Right? X equals square root of 8, which is always reduced to radical 2. Look at where it is. It's positive because it's over there. Positive x-axis. Oh. Well, that's just going to be adjacent over negative 1. So what's the answer to this? Negative 2 radical 2. All right. So when doing these inverse trig functions, you need to think through them carefully. You need to think through what's happening inside and what's happening outside. And keep in mind, sometimes you never actually have to find that angle. We were able to solve that whole problem without ever finding an angle. All right. Sometimes the inverse will be on the outer one. Sometimes the inverse will be on the inner function. Just keep in mind those restricted domains. Let's do another one. Let's do tan inverse. Sorry, I'm going to write that out. Tan 3 pi over 4. Okay? Always start with the inside. Stop yourself. Is it an inverse or not? It's not an inverse. I just want tan of 3 pi over 4. Great. There's 3 pi over 4. What is the reference angle? Pi over 4. Oh yeah, what's the ratios around pi over 4? It goes 1, 1, radical 2. That one's negative. And I need the tan of 3 pi. I need the tan of that. Tan is 1 over radical 2. So now I have tan inverse, positive 1 over radical 2, which we know is radical 2 over 2. Okay. Because I'm now looking for an inverse function, this is when you got to start thinking, but I'm restricted. Okay? My tan is restricted to quadrant 1 and quadrant 4. Quadrant 1 and quadrant 4. So is that ratio I'm now looking for positive or negative? It's positive. So you're going to draw the exact one in quadrant 4, and you can have your radical 2 over 2, or 1 over radical 2. What's the angle? Well, it's just pi over 4. The other thing I want you to notice, an inverse tan does not automatically cancel out a tan. All right, the answer was pi over 4. Because once you're doing the inverse, you can only draw it in these quadrants. Quadrant 1 or 4 for sine, 1 or 4 for tan, 1 or 2 for cosine. You cannot solve these problems without drawing the triangles. So please make sure you take the time to do that. Okay? That's it for your inverse. This is what I want you to be able to do for your inverse trig functions. Of course, I also want you to be able to use a calculator. Everything we did so far, answers will be give exact. So if you give me some crazy radian, you cannot plug these into a calculator to get these exact answers. You will not be able to use a calculator for any of these particular problems. The directions will state very clearly, give exact answers. Sketch the triangles around the coordinate system to get your answers. If I don't see that and you just use your calculator, you're not going to get any points for the problems. But then I'll say, hey, use your calculator to find each and round to, I don't know, 4 decimal places. Well, that's going to be different. Okay. Now I can say, hey, cosine inverse of 0.1578. When doing inverse functions, because you are given ratios and not angles, you have no idea if they're in degrees or radians. So I would have to say for each problem, put answer in radians. Okay, please read it carefully. If I say radians, whoops, put it in radians. If I say degrees, put it in degrees. You need to find that cosine inverse on your calculator. Make sure your calculator is in radians. And then plug in cosine inverse of 0.1578. And I got in radians 1.412. Okay? So take your time when utilizing the calculator and make sure you read the directions when dealing with inverse functions and plug it into a calculator. And make sure you have it in... on the test, I did check it. I tell you whether I want you in degrees or radians, so no worries there. Okay? Hopefully, when you do the lab, there's plenty of these problems on the lab to practice.